In today's world, many industries rely heavily on the computational power of computers. For instance, a civil engineer uses specialized software to design and analyze the structural integrity of a bridge, while an aerospace engineer depends on computers to ensure that an aircraft will fly safely and efficiently. Even beyond computers, handheld calculators can solve a variety of mathematical problems, such as integration and differentiation, making our university life much easier. Have you ever wondered how these devices can solve everything from simple math equations to highly complex systems? What kind of processes take place inside these technological tools? To explore this, in this video we will shed light on the world of numerical methods. To understand numerical methods, it is important to first distinguish them from analytical methods. Analytical methods are solution approaches that provide exact answers to problems. To illustrate this distinction, let's consider a function of x defined as the square root of x. Suppose we want to calculate the area under the curve from 0 to 3 using an analytical approach. To calculate the area under the curve, we need to evaluate the integral of the function within the given range. So our problem reduces to finding the integral of square root x from 0 to 3. Since the square root of x can be integrated analytically, we apply the basic integration rule. Finally, we obtain the result as approximately 7.794. We see that when a function is analytically integrable, we can directly obtain the solution. However, consider the case where the function of x is something like e to the power of negative x squared. This is an example of a non-elementary integral, meaning it cannot be expressed in terms of basic functions. Therefore, unlike the previous example, we cannot rely on analytical methods, and instead we must turn to alternative approaches. This is the point where numerical methods come into play. They are simply techniques designed to provide approximate solutions to problems when exact analytical solutions are not possible. To solve this problem using numerical analysis, we divide the area under the curve into small rectangles and approximate the result by summing up the areas of these rectangles, as shown in the graph. In addition, the approximation improves as we decrease the width of delta x, because the shape of the area becomes more similar to the actual curve as the rectangles get thinner. As a side note, this process is an example of a numerical method called numerical integration. After these explanations, we can now formulate the solution more clearly. We measure the area of each rectangle as the function value at the midpoint of the rectangle times delta x. Lastly, by computing the summation for a small value of n, we get the approximate area as 2.357, which is incredibly close to the exact solution. Let's examine another example to gain a deeper understanding of numerical analysis. In this example, we will explore the behavior of a freely falling ball and its velocity over time. We begin by drawing the free body diagram, identifying the forces acting on the ball at an instant t. At any moment, two forces act on the ball. First, the gravitational force, directed downward, equal to mass times gravitational acceleration. Second, the drag force, acting upward due to air resistance, denoted as F drag. Additionally, we can indicate the direction of the velocity as downward. Now, let's proceed with the solution. In the first case, we assume the drag force is constant. In this scenario, understanding two fundamental equations is essential. Net force equals mass times acceleration, and acceleration equals the first derivative of velocity. For the first equation, we can substitute F net with the corresponding value from the free body diagram and directly solve for acceleration. Then, we can obtain the velocity formula using the second equation by replacing acceleration with the previously derived expression. As we see, when the drag force is constant, calculations are straightforward. However, this assumption rarely holds in real-life conditions. Now, let's slightly modify the scenario to observe how the approach changes. In the second case, the drag force depends non-linearly on several variables, including time, temperature, which may vary with altitude, velocity, and others. At this point, we cannot directly write the net force because the drag force is non-linear. Here, numerical methods become essential. Instead of finding the velocity function continuously, we discretize acceleration and compute velocity over specific time steps, delta t. To do this, we first approximate the derivative of velocity as delta v over delta t, which allows us to discretize acceleration. Now, we have velocity in discrete form. Next, we can compute velocity at t plus 1. As we see, we can calculate velocity step by substituting numerical values into the equation. For example, we can determine the velocity within a 0.1 second interval. Assume that at the initial time, the ball's velocity is 0, F drag is 10 newtons, and the ball's mass is 2 kilograms. With these values, we find the velocity at 0.1 seconds to be 0.481 meters per second. This procedure illustrates numerical differentiation, allowing us to compute values without obtaining the full analytical solution. In conclusion, numerical analysis is a fundamental and powerful tool used across both the natural sciences and engineering. In this video, we have only touched on a small portion of the many techniques available, but even these examples illustrate how numerical methods help solve complex real-world problems. In the upcoming videos, we will dive deeper and explore many more fascinating techniques, including applications in physics, engineering, and technology. Thank you for watching and following along with this explanation. I hope it has sparked your curiosity and helped you appreciate the importance of numerical methods. Remember to subscribe to the channel and turn on notifications so that you won't miss any of our future videos, where we will continue to uncover new methods and their practical applications. See you in the next video, and keep exploring the world of numerical analysis.